Alright, so this is presentation 7 for ENGI 305. It's on reliability and survival. My name is Selassie, and then my partner is Jordan Stevens. So this is a quick overview. We're going to be looking at life distribution, recurrence analysis, and then survival analysis. And for all of those three, we're going to be using different data sets. Life distribution, we're going to be using the FAN data. Recurrence analysis, bladder cancer data, and then survival analysis, we're going to be using the RAT data. Alright, so life distribution. This life distribution is basically fit distributions to lifetime data. It helps to discover distributional properties of time to event data, basically analyzing the lifespan of a product, component, or system. And some pharmaceutical companies use this to be able to, basically most companies use this in all honesty to be able to determine how long, an item or product or commodity will last. And that's basically one way in which they set their expiration dates. And then we'll be going into Jump to look at how we can actually create a life distribution graph or a life distribution plot using the FAN data. Alright, for life distribution, we're going to be using our FAN data. And then what we're going to try and do with this is to check basically the expected or the life expectancy of basically the FAN. So we're going to go into analyze. Then over here we have our reliability and survival, and we're going to click on life distribution. As you can see, it says a distribution of time to event. So basically product lifetime. So we click on that, and then for this we're going to go ahead and put our sensor in the sensor column. And sensor is basically when all the observations are not known. So that's basically what sensor data or sensor, when they say a data is sensor, that's what it means. And then we're going to put our time in here. So we'll go ahead, click OK. And as you can see, that gives us a graph here. It's a life distribution graph with compare distributions. We have our stats down here, and then the summary of the data down here. Alright, so now that we have our compare distribution, we're going to go ahead and change the scale and the distribution to a log normal. And what you see is that our points fit well along the line. And somebody was asking, as you can see, the distribution profile also tells us the log normal and then the time. And so these are very useful for determining or setting expiration date or times on maybe products or, instruments. Alright, so for recurrence analysis, this basically models frequency of cost of recurrent events over time. It checks, the probability of repeated failures, or the probability of repeated failures to occur. And then the goal of whenever we conduct a recurrence analysis, we most often want to be able to obtain a mean cumulative function, because that gives us a graph that shows us that, okay, you can expect this number of failures at this point in time. And to show a graphical representation of this, we'll be using the bladder cancer data in Jump to generate that graph. Alright, so now we're going to look at the bladder cancer data, and this is what we're going to be using to show how to perform recurrence analysis. So data is already opened, so we're just going to go to reliability and survival, because that is what we're dealing with. And when we go on recurrence analysis, we see over there it just shows probable systems, so basically how a recurrent event is distributed over time. And then for this, we're going to have our age, and now it's going to be our event timestamp. Our patient number is going to be the label or system ID. We got to include cost, the cost column, and then we're going to group that by treatment. Right. Then we'll go ahead and click OK. What that does is that gives us an event plot, basically of the various treatments that we have. And then when we go down, we see our MCF plot, which is usually the goal of a recurrence analysis, because that gives us a better idea of how, let's say in this case, how the drugs are performing. So as you can see, they're all basically straight lines with just, I don't know if to call them jitters, but they fluctuate and then increase based on the age. And I mean, all of these are not that great, but at least we can say that Theothepa among these three is the best one. Alright, so next we have survival analysis. And survival analysis is basically duration time until the occurrence of a specific event. So we use this to examine the distribution of failure times. And these usually have specialized non-normal distributions. So like they usually have your exponential or your Weibull distribution. And then we'll be using the rat data and JMP to show how you can create a survival analysis. And then basically analyze the report. Alright, so now for our survival data, our survival analysis, we're going to be using the rat data. And then we're going to open analyze. Then when we're going to go to reliability and survival again. When we come down to our survival, we see basically older survival platforms supports groups. Click on that. And for this one, our time to event will be days. And then once again, we're going to have our sensor. And then we're going to be grouping by group. Click OK. This gives us a product limit survival fit. Gives us summary quantiles. And then test between groups. And as you can see, just as a reminder, it tells you what you selected or what you're basing your analysis off. And then, I mean, from this graph, we can clearly see that group 1, I believe, which is the red line, live longer than group 2, because as you can see, this is in days and this is their surviving. You can see that one stretches out. So group 1 lives longer than group 2. This is a way to basically construct a survival analysis in JMP.